All right, let's get into organic chemistry. So organic chemistry is the study of the structure, properties, and reactions of organic compounds. Now, what is an organic compound? An organic compound is a compound containing carbon atoms. Now, remember that not all compounds containing carbons are organic. For example, carbon dioxide, carbon monoxide, and metallic carbonates, or metal carbonates as you might call them, they are not organic compounds for conventional reasons. So, many of the structures that you will be drawing in your course are hydrocarbons. Now, what is a hydrocarbon? The term in itself, and that's the beauty of chemistry, is very self-explanatory. Hydro comes from the word hydrogen, and carbon, just carbon, right? So remember that a hydrocarbon is a compound that contains carbon and hydrogen atoms only. All right, so hydrocarbons are compounds containing hydrogen and carbon atoms only. Now we're going to learn a few formulas because you will be drawing, seeing, analyzing a lot of structures. There's 3 formulas that I want you guys to remember. First of all, we have the displayed formula. The word displayed is going to give you an idea of what we're going to talk about. Whenever you hear the name of a compound and you want to see the spatial arrangement of all the atoms and bonds in that molecule, you will want to see its displayed formula. I will draw a structure to help you gain an insight into what the displayed formula can potentially look like. If you examine this structure, you see that it shows you 2 things. The first important thing is that you see the atoms present in that compound, and you can see that it's only carbons and hydrogens. The second important thing that you see is the bond, or all the bonds present in that compound between all the atoms, okay? So the displayed formula tells us everything about the compound. If we talk about this specific compound, it tells us that this compound has 5 carbon atoms. It tells us that it has 12 hydrogen atoms, and it also tells us that this compound has only single bonds. And what is a single bond? This single line represents a single bond. And in other videos, we will learn what bonds are, what is a single bond, a double bond, so hang in there. The next formula that we're concerned about is the structural formula.
Excuse me, ma'am.
Yes?
Are we gonna learn how to read this?
Yes, sure. We're going to learn the naming of the compounds too. That is the next section, actually. That's a really good question, and I really appreciate your curiosity. In this section, firstly, we're going to learn the names of the formulas and the types of the formulas, and following in in the next few lessons, we will learn the naming of the compounds, different classes of organic compounds, and naming conventions of all of those types of compounds.
All right.
All right, now this next one is structural formula. As I mentioned earlier, the names are self-explanatory, and you can see that this type of formula is going to show you the structure of the compound. Now, in the previous one, you had an entire picture of the compound. In this one, there's enough information shown to make the structure clear, but most of the actual covalent bonds are omitted. So you don't see these single lines in that structure. Only the important bonds are shown. For example, the double bond or the triple bond, okay? And you can even put the identical groups into brackets, and side groups are also shown using brackets, straight chain alkanes, or other types of alkenes, which are the classes of organic compounds, are also displayed in a very nice way. So let me draw 2 structures in the displayed form first, and then we'll convert them into the structural formula, and you will see how the important information is not lost, yet the unnecessary stuff is omitted. We have two displayed formulas shown here, and now we're going to learn how to put them into the structural formula form. Now, you see, there's this carbon chain, and there are hydrogens on the sides. So I can write down every single carbon group, okay? So I have a CH3, I have a CH2, another CH2, another CH2, and finally a CH3. So I'm going to write it down. I have CH3, CH2, 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 and then finally a CH3. What I can do is that I can group these repeats into one bracket. So you see CH2, CH2, CH2. These are repeated. So what I can do is that I can write these CH3s on the sides like this. I can write the CH2 in the middle, and there's 3 repeats, so I'll write a little 3 as the subscript. So this 3 means that there's 3 CH2 groups in the middle. Is that clear? Okay, great. Now, how about this one? Now, did you notice that I omitted the single bonds in the above structure?
Yes, ma'am.
Do you think I can do the same with this double bond?
I guess.
So the answer would be no. And that is because not showing the bond is an indication that it's a single bond. But when it comes to a double bond, you have to make sure that you include it. Okay? Because that is the important information that needs to be included. All right. So now let's see the structures. You have one CH2 and another CH2. So I can write it down like this. CH2, CH2. And the important information to keep here is the double bond. Is that clear?
Yes, ma'am.
The next formula that you need to know of is the molecular formula. The molecular formula comparatively has less amounts of information. It only shows you the type and the number of atoms present in that compound. Okay? For example, if there is a compound that has carbons and hydrogens present, and there's 4 carbons and 10 hydrogens, then your molecular formula will look like this. C4H10. Or let's take an example of the compounds we've done above and write down their molecular formulas. As I mentioned, that the molecular formula just shows you the type of atoms present in a compound, and the total number of the atoms of each element present in that compound. First of all, can you identify which 2 types of atoms are present in this compound?
Hydrogen and carbon.
That's right. You have carbons and you have hydrogens. Can you count and tell me how many carbons there are present here?
5.
That is right. 5 carbons, 1, 2, 3, 4, 5. And how many hydrogens?
12.
That is correct. So this would be the molecular formula of this compound. How about this compound? Can you tell me the molecular formula of this compound?
C2H4.
That is right. C2H4. So you don't need to show the double bonds in the molecular formula. Now let's briefly discuss the idea of structural isomers. Structural isomers are compounds that have the same molecular formula but different structural formula. So the type and the number of atoms present in those two compounds are the same, but their spatial arrangement is different. What does that mean? Let's look at an example to understand that better. First of all, what's a structural isomer? Let's look at the table that will help us understand structural isomers better. So we have two compounds with the same molecular formula, C4H10. C4H10. I'm going to draw their structural formula, CH3, CH2, CH2, and another CH3. I'll draw the structural formula of the other compound, CH3, CH, CH3, CH3. So now I'll draw this plate formula to show this in more detail. So if I were to expand these, so CH3, I can expand it, and I can expand all of this as well. But I'll tell you how to expand the structural formula into a display formula. First of all, you can look at the carbons. 1, 2, 3, 4 carbons, so you can draw the carbons out. Now there's 3 hydrogens with the first carbon, so you can draw 3 lines and fill them with hydrogens. 2 hydrogens on the second carbon, 2 hydrogens on the third carbon, and 3 hydrogens on the last carbon. For this one, you have 1, 2, 3, 4 carbons, but you see the difference is that you see this third carbon in a bracket, and then another CH3. Now, this suggests that both of these CH3s are on the second carbon. What does that mean? It looks something like this. So what happens here? 1, 2, 3 CH3s on a single carbon. Is that clear?
Yes, ma'am.
Now, you see how even though the molecular formula is same for both of them, but their structures are different, and the displayed formula helps us understand the difference in their structures in more transparency. So now we understand that structural isomers are compounds with the same molecular formula. I'll repeat that. They have the same type of atoms in the compound and the same number of those specific atoms in the compound. What's different is their spatial arrangement or their structures. Okay?
Yes, ma'am.
All right. Now we're going to try another example to finish off with the topic of structural isomers. Now we have 2 more compounds. Their molecular formula is the same, but apparently their structural formula seems a little off. Can you see that the double bond in the first structure is between the last 2 groups? But in the second example here, the double bonds switched back and it's now between the second and third carbon, right?
Yes, ma'am.
Now, this switching of the double bond is what causes the difference in the spatial arrangement of the 2 compounds. I will draw out the structure of this isomer, and I want you to draw out the structure of that one following the one that I'm going to show. So I'll tell you the steps, even though we're going to learn drawing these structures and their naming and everything in the next section too, but I want you to get a little bit more comfortable with drawing them, so that's why we're starting even before we get to that section. So how do you draw that? If it's a straight chain, like you can see here, and there's no brackets, you don't have to worry about the different groups of atoms going into branches and all of that. So first of all, count your number of carbons and draw a straight chain of carbons. You have 4 carbons, so you can draw a straight chain of carbons, 1, 2, 3, and 4. And then it's very simple that you have to just fill out the hydrogens. Another important concept to follow here is that even though we'll be covering that in the chapter of periodic table, but it's essential here, so I have to bring it up. So the periodic table has the elements arranged in a pattern, and you would see that it has vertical lines and horizontal lines. The vertical lines are called groups and the horizontal lines are called periods. And both of these two give us some essential information. The group number tells us how many electrons are present in the last shell of that element. All the elements present in group 1 have 1 electron in their last shell. For group 2, there are 2 electrons in the last shell. How many electrons do you think are present in the last shell of group 8 elements?
8 electrons, ma'am.
Yeah, that's right. 8 electrons. Why is the valency of the elements important? It's important to figure out how many atoms are going to bind with that specific atom. For example, carbon is present in group 4. It has 4 electrons in its last shell. I'll give you one more point here to notice that every element or every atom wants to be stable. How do we define stability? We look at the noble gases. Noble gases are the elements present in group 8. They have 8 electrons in their last shell, and because they're noble, they don't react with any other elements. So every other element wants to be noble. It wants to be the great guy. So it wants to have 8 electrons in its last shell too. Now, since carbon, as I mentioned, is in group 4 and it has 4 electrons in its last shell, how many more electrons does it need to have 8 electrons in total?
4, ma'am.
Yeah, 4 more electrons. So it needs to have 4 more electrons. 1, 2, 3, 4. So to get 4 more electrons, what it does is that it bonds with 4 other atoms. And that is what you need to do. You would notice that every carbon has 4 arms. 1, 2, 3, and 4. And you need to give something into every single one of those arms. And we have hydrogens here. So coming back to what we were discussing, all of this was just like a side note. Oh, make it tiny here. So we were drawing the displayed formula of this structure. I mentioned that first of all, you draw a single straight chain of carbons and then you fill out the hydrogens. And I was mentioning how do you decide how many hydrogens need to be there with every carbon. With the first carbon, it needs to have 4 arms. Just remember this point. Carbon needs 4 arms. One of the arm of the carbon is with another carbon, but it has 3 empty arms. What do you think will happen here?
Ma'am, there would be hydrogen in front of all 3 arms.
Yeah, there will be hydrogens um, in all of these 3 spots. 1, 2, 3. How many hydrogens do you think I can place in the second carbon?
2.
2. Because you see 1, 2, 3, 4 arms. 2 arms are already occupied. You have 2 free spaces. We're going to put 2 hydrogens, 1 on each space. How about the third carbon? How many hydrogens?
2.
2. And for the last one, there's 3. So that is what you would do for a simple compound. Now, this is what the structure would look like if it had single bonds. But the structural formula tells us otherwise. It shows that there are 2 bonds between the last, there's like a double bond between the last 2 carbons. So what I'm going to do is that I will draw 2 arms here. Now, since there are 2 arms here and 2 arms here, we don't need this hydrogen, so I'm going to just get rid of it. And likewise, you have 1, 2, 3, 4 arms. So I don't need this one. I'm going to get rid of this one too. So students often make a mistake. They draw double bonds, but they end up drawing hydrogens in these spaces too. So please make sure that you don't make that mistake. Is that point clear?
Yes, ma'am.
Now I want you to take a minute, follow the steps that I mentioned, and draw the displayed formula for this compound. For recap, I'll repeat the points. You just look at the number of carbons, you draw a straight carbon chain, you draw any double bonds present, and then you fill out the rest of the spaces with hydrogens. Make sure that every carbon has 4 arms, no more, no less. Go ahead. All right, so this is the structure that you came up with. Let's see if it's correct. So you have 4 carbons, 1, 2, 3, 4, and you have 4 carbons in your chain. Excellent job. Then you had a double bond between the second and the third carbon. You drew that. And then every carbon was supposed to have 4 arms. 1, 2, 3, 4 for the first one. 1, 2, 3, 4 for the second one. 1, 2, 3, 4. And 1, 2, 3, 4. Excellent job. Here. Now we're done with structural isomers as well. We're going to move on to our next concept, which is homologous series. Now, homologous series, okay, it's a series, or you can say family of organic compounds. So different organic compounds, they're grouped or collected into different groups. They're like actually put into different groups. And those groups or families are called homologous series. You must have heard the name alkane, alkene, alcohol, carboxylic acid, etc. How do we put these compounds into one family? And the answer to that is the functional group. Well, we're going to discuss that in more detail as well. First of all, let's write down what a homologous series is. It's a family of organic compounds that have similar features and chemical properties due to them having the same functional group. That takes us to the next concept of the functional group. You see, functional. The word functional here suggests that this group is responsible for the functions of the compound that it's present in. Okay, so the functional group can be one atom, or it can be a group of atoms or multiple atoms, which are bonded in a specific arrangement that's responsible for the characteristic reactions or the properties of each member of a homologous series. Okay?
Yes, ma'am.
So the functional group is what is important to help you recognize or assign a family to a compound. Now, I'm going to write down different families that are included in our syllabus. They're functional groups and the suffix that their name ends with. I'm going to use FG for functional group. The first family that we have is alkane. Alkanes just simply have single bonds between all the carbons and hydrogens. We don't have a specific functional group here. It's like single bonds between carbons and hydrogens. And their names end with ane. Okay, you see? That is where this ane comes from. For example, you have methane, ethane, propane, and so on. The next one is an alkene. The functional group in alkenes is the double bond between the carbons. So this guy right here is important. What do you think? What is the suffix of alkenes? Like, what is their like name end with?
Yani.
Yeah, so this ene is called ene. So you will have methane, methane, propene, butene, etc. The next family here is the family of alcohols. The functional group, or the group of atoms responsible for the properties of this group or family, is the OH group. that is also called the hydroxyl group. And what do you think the name of alcohols end with?
HOL.
It's actually OL, all, or actually enol. That would be the better way to describe it. Enol. For example, methanol, butanol, and so on. The next family here is the acid family, or to be specific, carboxylic acids. The functional group present here is the COOH group. That's a huge group. And their names end with enoic acid. Next we have amines. We'll be studying every single one of them in detail, so don't worry if you feel like you're missing the details. Amine, you have the NH2 functional group, and the name ends with amine. Pretty simple. And lastly, you have esters. For esters, the functional group is COO. So their name has this format: yle and anoate. You'll see what this means when we discuss this family, but a little idea is that esters are actually made up of alcohols and acids. So one of them gets yle part and the other gets the anoate part, and those two combine to form an ester. An example of an ester would be methyl propanoate, okay? Now we want to know the general formula for these families. This type of formula tells you the composition of any member of a whole homologous series of organic compound. So if you have the general formula and you know the number of carbons in that family, then you can figure out the entire formula. Here we're going to write the general formula for a few of them. For alkanes, the general formula is CnH2n plus 2, and just represents the number of carbon atoms. All right, let's say that I tell you that the number of carbon atoms is 4. Then you can just plug in this number in the ends and get your formula. So you have Cn is 4, H2 and is 4 plus 2. Do a little bit of math. C4, H2 into 4 is 8, plus 2, 10. So C4H10. Do you think you can figure out the actual formula if you have the general formula and the number of carbons given?
Yes, ma'am.
All right, let's do one more example. I will give you the number of carbons and I want you to figure out the actual formula using the general formula. Let's say you have 2 carbons. Please do some working and tell me the actual formula of that compound.
I got C2H6.
That is correct. C2H6. Great. Now, the general formula for alkenes is CnH2n. I will give you the number of carbons and I want you to figure out the formula of that alkene. If you have, let's say, 3 carbons in an alkene, what do you think would be the actual formula of that alkene?
C2H4, H6.
That is correct, C2H6. Please make sure that you memorize these general formulas. Next, you have the general formula of alcohols. It's CnH2n plus 1 OH. And the general formula of acids is pretty similar. You have this entire thing this entire thing identical. So CnH2n plus 2 plus 1 is identical, but instead of OH, you have COOH. Okay?
All right.
Could you please figure out the formula of this acid that has 4 carbons in it? This is going to be a little tricky. Please make sure that you pay attention to the formula, okay?
C3H8O2.
Excellent job. You got it. It was a bit tricky. Let's draw out the structure. So first of all, you want to draw the COOH. COOH. Now there's a total of 4 carbons. 1 is already here, so you're left with 3 more carbons. 1, 2, 3. And you're just going to fill out this structure with the empty, with hydrogens and the empty spaces, and you will see that there's 1, 2, 3, 4, 5, 6, 7, and 8 hydrogens. Okay?
Yes, ma'am.
All right. Because if you eliminated this hydrogen and you put a 3 here, because the N here that you're taking is 3, since you're already eliminating 1 carbon.
Ma'am, N is 4.
Yes, N is 4, but we eliminated 1 carbon because it was present over here, right?
Okay.
So we took N to be 3, and when you plug it in here, 3 into 2, 6 plus 1, 7, but there's 1 more hydrogen here, so that gives you a total of 8 hydrogens, and this is the structure right here. So now we've learned that general formula can be used to work out the formula of a compound from different homologous series if we know the number of carbon atoms present, okay? And if you memorize these general formula and you're given the name of the compound, let's say they say that you have a compound named methanoic acid or propanoic acid. So once you learn the prefixes, we will learn in the next few sessions that the compounds, they have prefixes. What is a prefix? It's a word, a little word that comes before the main word. So for example, if you have propanoic acid, you know that there's a total of 3 carbons present. And the anoic acid part will tell you that it's an acid. And the word prop tells that there's 3 carbons. Once you've identified that it's an acid, you will draw out its general formula and you will use that number of carbon atoms to figure out the actual formula of the compound. Now, I want you to do one last example for this one. If I give you that N is 6, can you tell me the actual formula of that compound? Drawing out the structure might help.
C5H10O2.
Let's see if that is okay by drawing out the structure. So you said C5H10O2. I'll write down your answer first. C5H10O2. Are you sure?
Yes, ma'am.
Okay, let's see. So we know it's an acid. So I'm going to draw my COOH first and then the rest of the carbon. So there's 1 carbon here and 4 more carbons. 1, 2, 3, and 4. And I can just draw these arms for hydrogens. So there's 5 carbons, 1, 2, 3, 4, 5. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogens and 2 oxygens. That means your answer is correct. But I would like to make one little change, and that is to write the COOH separately, even though this is also correct. But it's always recommended to write down your carboxylic acid group as it is. So how will I change it? I'll write it as COOH, and on the side I have C4H9. Is that clear?
Yes, ma'am.
All right, now let's do some examples. What is the formula of an alcohol? Formula of an alcohol that contains 5 carbon atoms. So, could you please work this out?
C5H10OH.
Okay, so we have C5H11OH, and to confirm that, we can even draw the structure. First, you can draw your carbon chain, and then the OH group, and then you can fill out the rest of the spaces with the arms that show hydrogens. I don't draw hydrogens every single time in order to save time, and you don't have to draw that as well unless the examiner asks you to draw the structure because you really want your hydrogens present in that case. Right. So if we would use the formula, we would just have 5 here, right? 2 into 5 is 10, plus 1, 11, and then the OH. All right, let's do one more example. So the question here tells you that a compound has the formula C12H24, and you have to tell me the homologous series that it belongs to. Now this is reverse working. Can you guess the homologous series from the formula itself?
Can you please help me with that?
Yeah, sure. So you know that there are 12 carbon atoms, right? So what
Yes,
is the
ma'am.
value of N?
12.
12. And you can see that there is twice the number of hydrogen atoms than the carbon atoms. So this would be 2N. Therefore, the general formula of the compound would be CnH2n. Can you recall which compound has this general formula?
Ma'am, I forgot.
It's okay. Once you learn those general formulas, you will be more comfortable with them. So this is actually an alkene.
Okay, ma'am.
Now, finally, we're going to learn the general properties or characteristics of a homologous series. From all that we've done so far, we're going to just extract the summary of it. So now we're going to look at the general characteristics of homologous series. When we look at the trends over here, you can see that the families, all of these families, have their respective functional groups. So all members of a specific homologous series will have the same general formula, the same functional group, similar chemical properties, and a little difference in their physical properties, actually. And they will have a difference in the molecular formula between one member and the next of CH2. So the group that differs, or the group of atoms that is different, is CH2. And let's write those down. The point to remember is that all alkanes will have this general formula. All of the alkanes will have the same functional group, which is the single bonds between carbons and hydrogens. All members of a homologous series have the same general formula, same functional group, similar chemical properties, and slightly different physical properties. And the difference in the molecular formula between one member and the next, for example, between methane and ethane, is the addition of CH2 in the one following the prior compound. And the difference in their physical properties arises from the addition of that CH2 group. Because can you tell me what is a physical property? What do you think is a physical property? And how do you differentiate between chemical and physical properties?
Ma'am, I think physical properties are reversible and chemical are not.
Excellent explanation. So, chemical properties are the properties due to the chemical reactions between the compounds. And of course, the chemical reactions are irreversible. And the chemical reactions involve electrons in the last show, right? What really are chemical reactions? They're just like the gain and loss or the combination and sharing of electrons. So since these homologous series, these compounds have similar electron composition, their chemical properties are quite similar. But their physical properties, on the other hand, differ due to the difference in mass. When you add the CH2 group, more mass is added to the compound. Let's take an example to understand that. So if you have methane, and ethane. Methane is simply CH4. Ethane has an additional CH2 added to it, so it becomes C2H6. Now, the addition of this CH2 results in the increase of mass of this ethane molecule. What does that do? When you have higher mass, that means more energy is needed to break those bonds and cause the change of state of this ethane. So the addition of the CH2 group results in the increase of mass of the following member of the homologous series. And when you increase the mass, that means more energy is needed to break those bonds and cause the change of state. To go from solid to liquid and liquid to gas, you now need more energy. That is why the members of the same homologous series have slightly different physical properties. All right, so that was it for today's class. We learned organic formulas and homologous series. Now, a little recap of what we've done. We learned what an organic compound is, compounds containing carbon. A hydrocarbon has carbons and hydrogens only. Displayed formula displays everything, shows you all the bonds, the atoms, and every detail. Structural formula omits the unnecessary details, the bonds, but it retains the important information like double bonds. Molecular formula is comparatively very simple. Then we did what isomers are. We'll be doing more examples in following classes, but isomers are simply compounds with the same molecular formula but different structural formula, and we have a few examples here. And then we did functional groups in homologous series. We studied that homologous series are simply families of organic compounds that have similar features and chemical properties due to them having the same functional group. And we studied the functional groups of these families, and we also studied the suffixes that their names end with. And we did a few examples here that you can surely practice after class as well. And lastly, we summarized the general characteristics of a homologous series. I hope everything was clear, and I'll see you next time. Bye.